In this video, we're going to learn how to determine the electron configuration of elements and ions. So remember, energy levels are the rings that we find around the nucleus. So that's where we find our electrons. So electrons are found in distinct energy levels, and as you go out from the nucleus, the energy increases as you go further and further away. And energy levels are numbered. So N is equal to the principal quantum number. So the first energy level is 1, the second one, N is 2, 3, and so on, all the way up to 6. And those energy levels themselves are split into sublevels. So as I said, energy levels are divided into S, P, D, and F orbitals. So those sublevels. Orbitals indicate where there's a higher chance of finding an electron, and each orbital is subdivided to hold only 2 electrons. So example, the p orbital is divided into 3 suborbitals, so x, y, and z, and each of them are found 90-degree angles from each other. So this would be the probability of finding electrons would be in these orbitals here. So these would all overlap. So that's where you would likely find electrons in the p orbitals. In the s orbital, it's shaped like this. So it would be most likely to find electrons here. Each orbital can only hold 2 electrons, or each suborbital. No 2 electrons in an atom can have the same quantum numbers. Now, quantum numbers is beyond what we need to know for higher level chemistry, but what we do need to know is that electrons in the same orbital have to have opposite spin. So one of the electrons will be pointing north and rotate clockwise. The opposite one will be pointing the opposite way and rotating anti-clockwise. So this table from our Cognitive textbook looks at the energy levels and then shows the sublevels. So you can see here, when energy level n equals 1, there's only one sublevel. There's only one orbital, so s. And 2 electrons can fit there. So the maximum number of electrons in the main energy level is 2. So it fits our Lewis structures and our Bohr diagram model. When n is 2, there are 2 sublevels. So there's s and p. So 2 electrons fit in the s orbital and 6 fit in the p. So a total of 8 in period 2. The next energy level, period 3, or n equals 3, you have S, P, and D sublevels. So 2, 6, and 10 electrons can fit in energy level 3. So that's a total of 18. If you would count across on period 3, you would see that there's 18 all the way across. The next one, n equals 4, all the orbitals, because this is where you would splice in the actinides and lanthanides. So you have S, P, D, and F. So 2, 6, 10, and 14. So actually 32 electrons can fit in that energy level. So this is why after the second period and going down into like anything higher than 20, the Bohr model with 8 electrons fitting in each valence doesn't fit anymore. So there are a few rules that we need to follow. The AUFBAU principle says that an energy sublevel, must be filled before moving on to the next sublevel. And each sublevel has higher energy than the one before. For instance, you must fill the 1s sublevel before you start putting electrons in the second one, 2s. And then one thing to note, 4s has a little bit less energy than 3d, so we actually fill it first, and we'll talk about that in a little bit. So the way we write electron configuration, there's a few things to note. So we'll write the energy level with a number, then the letter, so which sublevel it belongs to, and then how many electrons are in that sublevel or occupying that sublevel. So if we do some of the first few elements, if we have hydrogen, I'll just switch over to my pen. If we have hydrogen, the electron configuration is just 1s1. Helium is going to be 1s2 because there are 2 electrons, so it fills up the energy level. The next one, lithium, will be 1s2. You'll notice that each time it's getting one bigger. Now we move over to our next energy level, N equals 2, so 2s, and then there's 1 electron. The next one, beryllium, is 1s2, and then 2s2. So number 5 is boron, so it's going to be 1s2, 2s2, that's the first 4. Now we're into the p sublevels, or p orbitals, so 2p1. And then carbon's next, so it's going to be 1s2, 2s2, 2p2. Then we've got nitrogen, 1s2, 2s2, 2p3. And then oxygen, it's going to be 1s2, 2s2, 2p4. And then we've got fluorine, so we have 1s2, 2s2, 2p5. And then finally neon would be 1s2, 2s2, 2p6. So it just follows that pattern, as simple as that. Now, you can write electron configuration in a condensed version. So you can actually condense your notation to start with the closest noble gas. So this is the electron configuration for sodium. So you'll see 1s2, 2s2, 2p6, and then 3s1, so sodium. That can be written with square brackets around the symbol for neon, and then just 3s1. So neon and then 3s1. So now we'll try a couple of examples. So if we take a look at magnesium, its noble gas ahead of it is neon, just like sodium. And then we're in the third period, or the third energy level, so it's going to be 3s, and it's in the second group, so 2. If we try potassium, it's the next group down, so, and its preceding noble gas is argon, and now it's going to be 4s1. And phosphorus is before argon, so it's going to be neon. And then we start working our way across the third energy level, so it'll be 3s2 because sodium and magnesium, and then 1, 2, 3, so 3p3. And then lastly, bromine. Bromine is just before krypton, so we would write Ar. And then this is, remember, where it gets kind of unique. So we do 4s2, and then remember the D group so is there because the transition metals are along there. So now it's going to be 3d10, and now we go back to the p orbital, and bromine is in the 5th position, so 4p5. So argon, 4s2, 3d10, 4p5 is how you write that one. Now, one thing that's kind of not so fabulous is there are 2 exceptions that IB requires you to memorize. So chromium and copper are the 2 that don't fit the model, but you don't need to know the reasons why, according to IB, because it's beyond what you can understand at this point. So you need to memorize these, but you don't need to understand why. So if you take a look, chromium is 1s2, 2s2, 2p6, 3s2, 3p6, but here's the wonky thing, 4s1, 3d5. So instead of filling this one, it only left one. The same thing for copper. So it goes 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. So just for copper and chromium, you need to know that there's only one electron in the s orbital for the level 4. You just don't need to know why. So for ions, you write the electron configuration the same way, but you'll add or take electrons away depending on the ion you're writing for. So if we take a look at sodium, so sodium has a +1 charge, so it's going to be isoelectronic to neon, if you remember. So we're going to write basically, because it's lost an electron, so now it's the same as neon, it's going to be 1s2, 2s2, and then 2p6. So it's got the same configuration as neon because it's an ion. It's lost an electron to become like neon. So if we try some examples, the first one we're being asked to do is draw the electron configuration for chlorine and then the chloride ion. So chlorine would be 1s2, 2s2, 2p6, and then 3s2, 3p5. It's almost at the noble gas position. But then the chloride ion would be 1s2, 2s2, 2p6, 3s2, and 3p6. So it's isoelectronic to argon. So the next one we're being asked to do is calcium and the calcium ion. So calcium is 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2. But the calcium ion loses 2 electrons to become just like argon. So we're going to write Ca2 plus is 1s2, 2s2, 2p6, 3s2, and 3p6. And then finally we're going to do oxygen and the oxide ion. So oxygen is 1s2, 2s2, and then 2p4. And then the oxide ion gets 2 more electrons to become like neon. So it'll be 1s2, 2s2, and 2p6.